Thank you, Eric, and thank you to all of you for coming by. So I'll tell you about our experiences with multiscale modeling using calcium as an illustrative system. But of course, the problem is much worse than just calcium. So here are some of the things that calcium does and that have to be accommodated in a reasonable model. So there are microdomains of calcium. There's interesting calcium effects in synaptic transmission. You're all familiar with what calcium does interacting with NMDA receptors and other channels. There are pumps, there are buffers, there are stores, there's diffusion, channels of various kinds. For the channels, you have to worry about the fact that calcium ion concentrations vary greatly, so you have to worry about Goldman-Hodgkin-Katz equations. And then, of course, calcium talks to signaling all over the place, which causes all sorts of lovely complications, and so on. So these are things that we would like to be able to model in the context of what the rest of the system is doing. So there's the network doing its thing, which is neurotransmitters and electrical activity and broadcast transmitters and growth factors. There's the cell, which has got the voltage and other biophysical events. And then there's the dendrite and spine and various kinds of specialized signaling that goes on there. And calcium is involved in all of these. And it's not just a one-way flow of information. It's not just that the calcium goes and tells the signaling molecules what to do, but of course the signaling molecules come back and redefine what the cell is doing. So a lot of stuff is happening, and we would like to model all of this, and this is my take on multiscale modeling is to be able to handle these kinds of processes. So this is an overview of what I'll describe, which is the technicalities some of the technicalities we've run into. Model definition, simulation, and input and output. So let me just begin right away with the model assembly problem. So let's do it in a simple way as I've been able to come up with, which is to say, here is a cell model, electrically defined compartmental model I want to use. And inside this, I want to embed some calcium dynamics or some signaling pathways. So here I have my electrical model, which is compartmentalized in some manner suitable for those calculations. And inside that, I have embedded a model with signaling pathways, including calcium. So here's some typical things, the usual set of channels and so on. So first thing when you assemble this is you need to have an idea of where the signaling pathways of your interest go. So for example, in this particular case, we had one kind of signaling pathway driven by calcium in the spines and another kind of signaling pathway in the dendrites. And of course, because I didn't have infinite computer power, unlike some people I could mention, I chose not to put the signaling calculations in the whole cell, and I only chose to model a few spines. And so we therefore chose a subset of the cell to do the signaling in. And it turns out then that when you do the calculations, you have to discretize this differently on a finer time scale than the electrical model, just to get the numbers right. And the way we set it up, or the way we could have set it up, is to use a NeuroML model file for specifying the cell, and a couple of SPML model files. So does everybody know NeuroML and SPML, these letters? Some people know. So SPML is Systems Biology Markup Language. That's good for defining chemical systems. NeuroML is one of the standards that is used for defining cell models, neuronal biophysical models. Or you could use stuff from Genesis definitions, which is another possibility, which is what the earlier version of this actually did. And so this is the first stage of setting it up. You take your reference models and you now place the chemistry inside the cell physiology, the electrical model. And right away you run into some interesting problems. So the ideal thing would be you just look at your neuronal model and you say, okay, this defines the geometry, in fact, in a very concise manner. And you just spread your chemistry through this, perhaps with saying that I want the spines to have some form of chemistry and I want the dendrites to have some other, and maybe the soma should do something else. But now when you get into the details, you have to ask yourself, okay, now what really happens at the junctions between the compartments? For the sort of pseudo one-dimensional branching framework that you have for neuronal modeling, for electrical modeling, no problem, right? You just have them sticking into each other in some conceptual manner. But if you're going to do chemistry, specifically diffusional chemistry, you now need to make sure that you don't have any holes. You shouldn't really have sharp edges, because that does weird things to your diffusion calculations. And so, as you see, I ended up with a kind of a android robot-like cylinder with a round head with some more antennae sticking off it, and one can in principle do this. But you have to have some kind of a understanding of a standard saying that this is how you will treat junctions if you want to be able to do these calculations accurately. It's not so bad if you're doing pseudo one-dimensional diffusion calculations, but the moment you go into three-dimensional reaction diffusion stuff, this matters, and it makes a difference to the outcome. Okay, and you would like, of course, to be able to be smart and do this automatically. We're not there yet. I don't know if anyone is there yet to decide what is a good way to subdivide it and to tell the computer that this is a good general way to do it. So at this point, you look at it and you decide, okay, these are the resources, this is the amount of accuracy I need in space. And so you have to actually tell the computer a lot about how to discretize this. Okay, so that's one of the interesting things we ran into. Next, mapping variables. So this is, in principle, a straightforward thing. That is, you want to map the biophysical quantities of current and, well, particularly of current and conductance, back and forth between the chemical parameters of concentration and concentration, or molecular numbers. So, for example, the channel current, in particular the calcium thing, has to be mapped to through the Faraday's constant and whatnot to concentrations. And already you run into interesting details, like the fact that your compartments are discretized differently. So you probably want to make sure that the boundaries are the same, but anyway, there's some interesting issues there. When you do channel phosphorylation, that's again relatively straightforward to do. You say that here is form A of my channel, the unphosphorylated form, here's form B, and you give them different channel kinetics, different conductances, and so on. And then when you run the calculations in the chemistry, you just have the two forms, phosphorylated and non-phosphorylated, and map these onto conductance terms.
Let me ask about this diffusion of calcium inside there. Is it well established, or is it isotropic?
We're not making any assumptions about that. So it just depends on the level of detail you want to go with. I mean, it's clearly not straightforward, because you have microdomains and interesting things happening very close to the membrane. All I'm saying is that these are issues that crop up even with the simplest decomposition.
My question was not really about, I mean, it's more about what is known about physiology.
Yeah.
About
right. So in terms of physiology, it's clear that there are some weird things happening. So when you have a channel, the local calcium concentrations near it are very, very high. And the extent to which this affects physiology, well, it clearly affects it a great deal in spines and presynaptic areas. I've had information from colleagues who say that very often the cell behaves as if there are actually two or more distinct calcium pools doing different things in the same compartment, based on the effects of calcium pool A on channel type X and on a different channel. So I think there's a lot of very interesting stuff happening there. I'm just saying that this is the general framework. You have to deal with these things just to begin to start to model these effects. Okay, so now how will you define your model? So start off, I'm not going to go to many cells, though in principle this could be extended that way. So you want to define neuronal biophysics and geometry. So NeuroML is currently the obvious place to go with that. For chemical models, you would probably use SPML, though there are alternatives. How do you embed chemistry in the neuron? Now, at this point, LEMS and other abstractions notwithstanding, there is no standard way to do this. At this point, what we're doing is as I said, we just grab different models, and using straightforward Python scripting, we just say this goes here, this goes here, this goes here. This is not a standard. This is just what works for now. And so this brings me to, I think, one of the the key points that I would like to present here, which is, do we need another modeling language, a markup language, to specify chemistry embedded in cells if you were trying to do this kind of model? Or is it something that can be done in existing frameworks? So what can and cannot be done using SPML, CellML, NeuroML, LEMS, or 9ML? So I put together a little table, and the danger of putting up tables like this is that people who are associated with any of the things on the headings start to complain that, no, we can do that, we can do that. So I have to...
Can you say what LEMS is?
LEMS is low entropy model specification. Is that right? Hey, I got it right. Huh? So that's one of Robert Cannon's, one of the things he's unleashed upon the community. And I don't know whether it's yet formally in the level 2 specification or not, Pareg.
It is, yeah, the basis of NeuroML is the model definitions are specified in those, but you can still use the top level NeuroML definitions.
Okay, anyway, so here's a little table, and I'll just run through it really quickly, which is that, yes, you can specify complicated geometry neuronal models, certainly with NeuroML. In theory, you can do it in SPML, and Nicolas Lenover has made this amazing thing where he's actually defined the entire Hodgkin-Huxley squid model in SPML, and it is something which should not be done. It can be done, and it's a good proof of principle, but don't do this at home. It's not safe. Yeah. So yeah. So I think this is this is one of the realizations that there are good things to do with certain definition languages. That's what they're meant to do, and you can twist and contort things to get things to work in other formalisms, but it's not efficient, and it's probably not the right way to go. And that's important for this discussion, because what I'm leading towards is what is a good way, what is an appropriate way to define models which have both the chemistry and the electrical parts. Anyways, so you can define the complicated geometry in various ways. You can define chemical reaction diffusion. Now that's squarely in the domain of SPML. There are three-dimensional extensions. It's not yet fully formalized, but certainly, where's Ion? Ion is up there. Certainly the group at Connecticut have been able to do this and have their own formalisms, and Jim Schaff there is busy trying to get the formalisms set up for SPML.
What is it an extension from? 0D?
Sorry?
Actual extension of SPML.
It's a SPML extension.
Before it was extended, what was it?
Well, I think it's very strongly based. It's very strongly based on eCell.
Yeah, it is. So basically, SPML decided that with level 3, you're not going to have a single standard anymore, but they will be all called extensions to extend the formalism of SPML to specific domains. Say for flux balance analysis, for spatial descriptions, for multi-states, multi-components, because it was realized that there will be no single fully compliant tool left if everything will be dumped in the form. So that's why they're called extensions, and one is for the geometry.
Yeah.
But it's still an extension of the script.
Yeah. So yeah, thank you. So that's basically where it is. But I should point out that although it's a great definition, it's still a work in progress. But I would make the case that it's actually not appropriate for doing neuronal models, because you already have the geometry for neuronal models, and it's actually a very nice and concise definition of the geometry, and it's probably simpler to inherit that and use that for your chemistry rather than do this rather detailed thing defining things in terms of tessellated surfaces, which is what the definition currently relies on. Yeah. So anyway, so there are 3D reaction diffusion systems which you can do in SPML, but maybe not the way to go. How do you map between chemistry and electricity? There are ways to do that. I think LEMS can do that, right?
Can to a certain extent, yeah.
But there are these compartmental juggling things that don't. Anyway, there are these issues. How about network connectivity? Well, 9ML has sort of nailed that one, but NeuroML does it too to a good degree. Numeric choices. How do you define whether you want to use single particle Monte Carlo reaction diffusion calculations, or whether you just want to treat things in a Gillespie or even a ODE manner? I don't think those choices are yet available in any of these formats. How do you build up a model from building blocks using Lego-like assembly, which is what I just discussed? I don't think you have that capability yet in any of these. But interestingly, you have the SPML has another extension which allows you to do this, but it doesn't really work for neural geometries. LEMS, again, in principle allows you to do this, but I don't know how it would fare if you threw this. Anyway, we should discuss this. And likewise, for 9ML, it would be interesting to actually try and implement something and see how difficult it gets. But anyway, we're just at the start. So what you would like from a standard is that it's declarative. In other words, you don't have to worry about any procedural implementations. So you just have it say this is the model and then let your simulator upload it. It would be nice to have a single model file. This is not difficult to do. XML base seems to be everybody's favorite. It should be terse, which is of course not something which you'd normally associate with XML. And it should be human readable and writable, which is something which is definitely not typically associated with XML. But you know, you can't have everything. Robert Cannon thinks you can go some way towards this, but anyway, it's something to aim for. So
why do you want a single model?
because because things get messy if you have multiple files, is my experience.
But at one side you kind of say you want building blocks, and to me like that is often the natural building block that.
Oh sure. So what I would let me rephrase that. I would be very happy to say that okay, this block of this file is SPML, this block is NeuroML or 9ML, and this block is something that glues them together, right? So, but I don't want to. It's just that my experience is that if you have different distinct model files, you can end up with mismatches, which then make things go all over the place.
Well, if you use a good repository, you know, you can get
yes. Anyway, yeah, they're
the technology to handle.
Yes, they're right, but no technology is idiot-proof or user-proof even. So let's let's just leave it at that. I prefer to have a single model file. It's not to say that that's what I have at this point, but I would like to go there. Anyway, so this is my inclination, at least for starters, that we do need to have something distinct to do this, simply to get the show off the ground. Right now we're using Python scripting, but I think that there's enough stuff there to that it will be a separate problem domain. Simply because yes, you can do things within existing domains, but sometimes it's excruciatingly painful and it's simply inappropriate to do it that way. They're not designed for it. But you know, all of this is stuff that will evolve. I think that this is where one can get started. Okay, so anyway, this is just something I'm throwing up for discussion about how do you specify these models. So having brought that up to your notice, let me move on to some of the fun and games we have with simulations. So the numerics, and this is a familiar chart and a familiar figure, in fact, of the brain. We would like to model everything from molecules to the whole thing, to the whole brain, and everything in between. So here are some of the major equations which belong in here. I should point out that I'm missing mechanics, which is increasingly becoming something of great interest, and hopefully we'll have more discussion on that. But anyway, chemistry is defined here: diffusion, Nernst potential, Hodgkin-Huxley forms, and even some of the standard synaptic transmission forms are in this little table. So this is how we attack it. We use a local large animal for this purpose. This is actually a photograph taken in Texas. I don't know how a moose landed up there, but evidently it did not fare very well in the process because it was stuffed. And so we do modeling across scales using MOOS. MOOS stands for Multiscale Object-Oriented Simulation Environment. And as you'll see in a moment, it's one of its goals is to get numerical engines to talk to each other. And by doing this, it is able to do things all the way from single particles, using Smolden as the engine for that. Compartmental, ODE, stochastic, and even now diffusion, reaction diffusion calculations, cell stuff, and network stuff. So all of these are things that we can do in MOOS. Its architecture, for what it's worth, is a sort of an object-oriented representation of the biology, but this object-oriented representation is taken over by numerical engines which can do different things with the objects, and then communicates in various interesting ways. Okay, and so here just something all of you know. The electrical model is basically the standard compartmental representation. Again, the standard backward Euler elimination kind of calculation. And chemistry, we use, again, a similar compartmental decomposition for the simple reaction diffusion systems. Here we can use, as I said, a wide range of numerical methods. So now let's get to one of the interesting hiccups that we've run into, which is timescales. So electrical timescales for doing these calculations of the order of 50 microseconds. I've written milliseconds. This is what happens with Greek letters sometimes. So it should be 50 microseconds. And the action potential communication time is of the order of a millisecond. In chemical systems, with the exception of calcium, and of course you cannot easily ignore calcium. In fact, my whole talk is supposedly about calcium, but most of the timescales there are of the order of seconds and longer. So you have a very wide gulf of timescales, and actually these become fairly nasty, stiff systems. And so you typically have a variable time step numerical engine behind this. And so what do? You have your biophysics chugging along at 50 microsecond steps, and your chemistry will do its own thing. So what we have ended up doing is to just say that every millisecond or so, we're going to get these things to talk to each other. You don't need to have them. You don't need to have the chemistry talking at 50 microsecond intervals to the biophysics. That's simply inefficient. So every millisecond or 5 milliseconds, they talk to each other. And what this means is that the calcium concentration in particular is updated for the benefit of, or the ion flux is updated for the benefit of the chemical calculation. And the channel conductances are updated for the benefit of the electrical calculation. So that's, that is completely ad hoc. It turns out to work. It doesn't matter whether you use a 1 millisecond or a 5 millisecond interval. We haven't really pushed it to longer intervals than that. It gives you essentially the same results. But I stress that there's no mathematical proof that this is right. And in fact, if you did do a mathematical proof, you'd probably find out that it's wrong. But anyway, this is something which would be worth getting clearer input on. So another interesting thing with calcium is that since you have these fast time scales, should you compute the calcium dynamics in the biophysical subsystem, in the biophysical solver, or should you compute them in the chemical solver? And there are pros and cons. So electrical solver already works with a 50 microsecond time scale, so great, you should use that. And it, of course, maps directly back into the channels, relevant ion channels. So that seems to make a good case for it there. But the moment you want to get into serious detail, which is where I actually started out this discussion, then you discover that it gets really, really messy. It's something which is naturally defined in a chemical formalism and not so naturally defined in the electrical formalism, simply because the electrical formalism is optimized for certain things, and the chemical one is optimized for just the sort of things that we are dealing with for calcium: diffusion, bumps, buffers, and all of that kind of thing. Okay, so here again is a trade-off when you're doing these kinds of things. If you have a nice, cleanly delimited system where the limitations of the electrical solver are not going to cripple you, that's often more efficient. But the chemistry solver will take care of nastier cases if you need to. So what are solvers? These are basically numerical engines which can be pretty much anything. The way it works is that, at least in MOOS, we define all the concepts as objects. So you have an object representing a molecule, another object representing a reaction, yet another object representing a compartment, say, or an ion channel. And this is what the user sees, this is what the interface sees, this is what the file I/O sees, this is what the program that loads in the model using SPML sees. But under the hood, and I've forgotten who coined the term zombie in the good old Genesis days. This dates back from Genesis, the use of Genesis, not the book of Genesis. But anyway. So the idea is that you have what looks like your good familiar old object representing the biological concept, and the soul of this object, in other words its actual calculations and even its parameter storage, is taken over by whatever numerical engine you choose. And this, I think, is a really good way to do this, because it preserves your interface, your programming and your user interface, while allowing you to do whatever you like under the hood. And for example, let's suppose that I have a molecule, say calcium, and I choose to initially to compute its values using some ODE solver. And I can do that and update the values in this ODE solver. Now supposing I change my mind and I say I want to have exactly the same model, except I want to solve this using Smolden, which is a single particle reaction diffusion system. So my original object that represented the calcium concentration is still there. And you can extract the calcium concentration if you desire. But it also now has, in addition, fields which tell you the coordinates of every single calcium ion that is floating around. Right? So you have exactly whatever you were used to interfacing with earlier, and whatever additional you need to deal with the additional complexity of the solver. So this I think is a good way to do this. It's the way we have used it. And so here are just some of the options we have for using the chemical solver. You can use nothing. In other words, it defaults to the built-in method. It uses any of the GNU scientific library methods. It can use Gillespie calculations, Smolden. It can do some of these in spatial reaction diffusion coordinates, and so on. And how do you interface between these? This is another whole layer of fun and games, which is, again, comes back to the problem of defining of the standards. How do you define how these things talk to each other? You need to map entities that are being solved in different domains. So channel conductances, how do you map the concentrations to that? So there you need mapper objects. You need ways to do fancier conversions. For example, you might need to do something to do the GHK calculation when you're mapping from current to concentrations. And you need things for mapping between different kinds of numerical techniques. So you'll hear discussions in due course about how you can use completely different simulation engines. In other words, not just solvers, but completely different tools, and use communications at the level of music or NPR or something to talk between them. So that too is something that is feasible, but that doesn't do away with all these specification issues. These issues are still there. You still need to have adapters. You still need to have ways of interfacing the concepts, of making mappings between the different domains. Okay, how do you specify how the thing runs? This is easy. You use Python if you're using scripting, and you use sedML if you're going to do it declaratively. So I'm a recent convert to Python, but it's really good. And if you aren't using it, maybe you should. Yeah, no, jokes aside, yeah, you can use whatever scripting language you used. For years, I've used the Genesis scripting language, which should be close to the worst ever thing. Since I was involved in saying that we wanted that, I can share the blame for that. Or sedML is actually the other declarative alternative. I was looking at its specification. It's very clean. It's very complete. It was designed to work with systems biology type simulations, but it's very general. It basically allows you to specify whichever simulation entity you want to control. It allows you to specify how you want to control it, and you can do this in very clever iterative ways within a declarative framework. It allows you to specify transformations for analyzing the output of your simulation. It allows you to specify even what you ought to expect from the simulation to see if you're getting the right answer. So it's really a very nice general thing, and it should work fine for any system set up using a modeling language type, markup language type framework. So it's very. I strongly recommend this as a way to specify how you built Figure 4a in your paper. This will very cleanly encapsulate all of that. Okay, so I'm now moving on to the last phase, telling you about input and output. So here's where there's an interesting impedance mismatch, and this colorful diagram is meant to represent the tortuous process that I typically go through doing this model development, right? So I start out sketching out my model outline on a piece of paper, and then in order to build and edit my electrical model, I start out with VI, though I'm sure some of you are of the Emacs persuasion. And I use Python, and I set up the electrical model, and I run it through Moose, and I get some graphs, and of course I go through this cycle many, many times to get the model that behaves the way I like it. And I do something similar with the chemical model. In this case, I use the Connecticut interface. Hopefully Moose will have its graphical interface complete fairly soon, so I can do the full process within Moose. That's where I would like to go. Then I do the calculations, then I look at the graphs, and I go back again many, many times to make sure that's behaving. Once I finally got two models, or multiple models that behave the way I like, I get all those model files, I have my master script, I run that to make sure it does the obvious things right, and then I now need to tell it to do a whole bunch of sweeps. I may need to do parameter sweeps to check parameter sensitivity. I may need to do stimulus protocol sweeps, giving it different kinds of inputs and seeing that it behaves the way for all of them. Or I might simply be running something stochastic, in which case I have to run it 1,000 times to make sure that I have the statistics of what I've been doing. And then I need to run this through some presentation software and figure out how to encode this all in ZML or whatever. Yeah, so there's a lot of stuff going on here which is actually a total pain to do. This is something which this is why I'm calling it an impedance mismatch. So this is something which should really be simplified and done within an interface. And someday, hopefully, we will have all of that happening. Here's the current state of the Moose interface. We also have OpenGL, but I haven't got the drivers for it on this laptop. So we can look at your model in nice 3D and make it rotate and other good things. Okay, so one would like to be able to do all of these steps within the interface to make it more friendly. Right. And finally, I have just one more slide for storage and visualization, which is actually just to plug the efforts of the INCF for some standards in the physiology field, which I think are actually extremely appropriate for bringing to multiscale modeling. That is, you just, after all, you're trying to model biology, so you may as well use the data formats that are used for storing biological recordings. So there's a whole bunch of standards that are already being built. Thomas Wachtler is one of the people doing this. There's an HDF5 compliant format that's being set up for this. And I think it's very, very close to being able to use for simulation things. Porek.
Neo that people are using?
Sorry?
Is it Neo?
That is related to it, yeah. Neo is one implementation of the API standard that you're referring to, that is NeuroShare based.
So there's an API which can talk to the existing standards which various hardware vendors have come up with. So that allows you to read those files. But how would you like to store your future files? I think that in HDF5 format, which is clearly defined, is a good way to go.
Since Neo has been mentioned, NeoScope is somewhat different. What Neo actually provides at its core is an object model for physiological data. And what the Neo software package includes is a library to read NeuroShare files. And whatever is compliant with the NeuroShare API, all vendors that are compliant with that, you can read in, and to some of you can actually even write.
Anyway, so you should be able to do this for simulations too. Why not? We have been talking to this team. We have something called Moogly, which is a standalone package for reading something very similar to this format, and which will converge very, very soon, to allow you to display single cells and click on any of the locations to see action potentials and whatnot, or for the matter calcium concentrations. Or you can look at cell layers and again do the same thing for the cells. You can of course do marvelous things like look at it in 3D with those funny goggles, and you can have little movies set up. So anyway, lots of fun toys that you can do, and this is something which we actually developed for our own simulations, but I think it's something which may as well be widely used.
In Python?
No, this is done in C++ with I've forgotten the library. It's one of the libraries that talks to OpenGL underneath. So this library is really nice. It provides a lot of the nice things, the stereo and the movie building capabilities. Yeah. Okay, so that really is it. I think what we really need to achieve in order to do all the wonderful things we'd like to do for multiscale modeling, we need to have good ways of defining models, which means standards. We need to have good tools for being able to do the calculations. And there's some mathematical elements there. There's a whole lot of computer science elements there. And we're trying our own little bit with the Moose project. And not to be forgotten, we need a lot of techniques for getting data in and out so that we can interface with it. And I'll leave you with one thought, which is that actually all of this is a small fraction of what's really going on in the field, which is that you need tons and tons of data for making any of these models. And that feeds, of course, into the standards and the data sources parts, particularly over there. We really have to make it so that it's easy for people to interface with all the tools that we're coming up with. That's partly why we're all here. And I think that's something that we should be aiming for in this discussion. Okay, so Moose is designed to do a lot of the good things to make this work, and we like stealing your code. So if you have some nice solvers, we would be very happy to adopt them. And yeah, so it's just one tool, and thank you all very much.